Okay, so this is Engineering Statistics and Linear Algebra, 18 EC 44, Module 1. This should be Lecture 6 because we finished in the last class the characteristic functions. Today we'll take up the functions of the random variables. So, what we call, if we consider the functions of the random variable, it just means that you have a function of the random variable. Might be which might be some g of x or might be phi of x or whatever you call it. Each one will just correspond to a function. So here, if you see here, the what you call function can be represented by y equal to gx. Function of a random variable can be represented by y is equal to gx, where g dot is some function. So using this, we can map all the observations of the Sx concerned with x into a new region of the real line called Sy concerned with the y. So we see that the y is equal to gx is generally, this type of functioning is generally used in many of the applications such as amplification, level shifting, clipping, or finding a power. All these are different applications. Or finding a power will be similar to taking a square of the voltage. So if we know the original fx, if we know the what you call PDF of the variable x, then we can, using the function which is the g of that operator, whatever we have used in ygx, we can easily find the PDF of the y. Known the PDF of x and the function gx, we can find the PDF of y, which is fyy. And of course, once you know the PDF, you can always find the CDF also. Okay, but there's a condition here, that is, this will be there only if there is an inverse existing. That means if we have x is equal to g inverse of y, then only that is possible. That is, finding fyy using the fxx and g is possible only if there is a inverse existing. If the inverse does not exist, then the only solution for that will be to take up the piecewise linear combination. Okay, so we might consider the piecewise section of gx in case the inverse does not exist. So we begin with the case where both a function and its inverse are available. That means we'll, for example, we'll just take the y is equal to ax plus b. In this case, it's possible to write x is equal to something else also in terms of y. That is the inverse. Okay, so here we will take that x is an arbitrary random variable, and we know the PDF and the CDF of this function x, and we represent y is equal to ax plus b. Then at that time, you can take b over here and then a over here, then you'll get x is equal to y minus b by a. Okay, you'll get x is equal to y minus b by a, where we can assume here that a is greater than 0. Okay, a is greater than 0. So the typical plot of that, whatever equation we have written, y is equal to ax plus b, or x is equal to y minus b by a, can be written something like this. So this is y is equal to ax plus b, and the x which is there here is y minus b by a, which is the inverse of this function, whatever we have written here. So we have region which is above the what you call y-axis, and below the regions along the y-axis and the x-axis that map into each other. Okay, that map into each other. So region where y is less than y, and region where x is less than x is what we can consider. So once we do that, then we can try to find out easily the what you call fyy, which is p of y less than or equal to y, and this p of y less than or equal to y will be x less than or equal to y minus b by a, because we know that from y equal to x plus b, we are able to find x is equal to y minus b by a. Okay, small x is equal to y minus b by a, and that is what we are trying to substitute over here. Remember that this is the CDF, not the PDF. It's still not the PDF, it is the CDF over here. So fyy is equal to fx y minus b by a is the case over here. So the equation expresses, if you will, so this is inverse, conservation of probability principles. This is just conservation of probability principles. If you have a function of y is equal to gx, then the probabilities of both x and y will be same, and that is conservation of probability principles. Okay, the probabilities are concerned through the mapping of the observations using the inverse function. So having the CDF there, we can easily find the PDF. So PDF is, you need to take the differentiation of both of them with respect to dy. Remember that it is a differentiation with respect to dy, y on both the sides. Okay, differentiation of this as well as this with respect to y on both the sides. So if you take that, you'll get here for this, you'll get the PDF itself. For this, you'll get the PDF, but again, you need to write the internal derivative of this. Internal derivative of this will be 1 by a. Okay, where again the one is a is greater than 0. So let us take an example here. Suppose the transformation 2.71 is applied. So we are trying to apply the 2.71 transformation, which might be there. Okay, let us not go deeply into back there. So that is x equal to sigma x z plus mu x applied to the normalized Gaussian random variable z, which is the transformation is this. Then for a normalized Gaussian random variable, we will have mu z equal to 0 and sigma z square is equal to 1. So that is mean is 0 and variance is 1 for a normalized Gaussian random variable z. Okay, z is the normalized Gaussian random variable. From that, we want to find the probability of x. Or you can say that the CDF as well as the PDF of x, known the PDF and the CDF of z. So it follows that x is having a mean, which is mu x, and variance of x is naturally sigma x square. So at that time, the fxx, this is the, now we have a function which is x is equal to g of z. This is like x is equal to g of z. So fxx is equal to fz x minus mu x by sigma x. Okay, and this is nothing but in terms of the phi, also you can write phi of x minus mu x by sigma x, where phi z is the CDF of the normalized Gaussian random variable. From the 2.99, you can easily write, that is, if you just differentiate on both the sides with respect to x now, right? Because it is, I have told you x is equal to gz now we have. So if you differentiate it with respect to x now, then you'll get fxx is equal to fz of x minus mu x sigma x, and internal derivative of this with respect to x will be 1 by sigma x, and that is what we have written over here. So that will become, in addition to whatever we have here, I will get 1 by sigma x also. So plot of a typical PDF and CDF of the what you call whatever equation which we have written is shown in the figure 2.11. In the figure 2.11, we note that the mean mu x locates the peak, and the peak or the mode of the PDF plot. The value of the PDF at its mean is this value. So this we will see here, right? It looks something like this, and also fxx will look something like this. This is the PDF and this is the CDF, which will look like this and this. So at mean, you will have the what you call the value of the PDF at its mean will be fx mu x will be equal to 1 by root of 2 pi sigma x, which just corresponds to this value. Okay. So that means at mu x equal to mu x, at x equal to mu x, this will become 1. And once this becomes 1, we are left with only this term, and that is what we have written over here. That is what he means by telling the value of PDF at its mean. That is, when x is equal to mu x, this will turn out to be 0. E to the power of 0 is 1, and we are left with this, and that's why we have that. Okay. So when the standard deviation sigma x is relatively small, the PDF at its mean is relatively large. That is what it shows because it is inversely proportional, and vice versa. And recall that the area under the PDF must always be 1. Area under the PDF will always be 1 because it corresponds to the total probability. So therefore, a small standard deviation gives a PDF curve that is peak at its mean, and a large standard deviation gives a curve that is flatter. So if you have standard deviation which is what you call small, then you will have it as a what you call steeper curve, whereas if the standard deviation is large, then the what you call width will be larger. Okay, width of the Gaussian PDF centered about its mean will be large. So when dealing with errors modeled in the Gaussian random variable, it is convenient to consider 1 by sigma x, the inverse of the standard deviation, as a precision, that the system has greater precision if sigma x is if the sigma x related to system error is small. So better precision if sigma x is what you call the sigma x is related to this what you call system errors is small. If sigma x is small, then precision will be better. So let us take an example here. A production drawing specifies a dimension on a just a minute, I'll just pause. So a production drawing specifies a dimension on a PCB of this, right? So this is the range of the what you call dimensions of the. So on the one side it will be 0.72 minus 0.002, that means 0.748. On the other side it will be the plus sign, that will be 0.752. That's why we have the range here. Okay, 0.752 and 0.748. Okay, so assume that the process that manufactures the device is such that the dimension is a Gaussian random variable. We'll consider Gaussian random variable, and the manufacturing process is accurate. We'll consider that. Our manufacturing process is quite accurate with the what you call mean equal to 0.75 centimeter. Also assume that the precision of the manufacturing process is such that the standard deviation is this value. So we are interested in finding the percentage of the printed circuit boards having the dimension within the specified tolerance limits, that is within this range. From this need not be given. Once this is given, this can be easily found out, right? So this might not be part of the question at all, because only this, and this will be part of the question. Okay. So this is nothing but the value of the capital FYY. Okay, in terms of the total probability is what we need to find out. The percentage of the printed circuit boards having the dimension within the specified tolerance limits is this. Probability of 0.748 less than y less than 0.752 is equal to Fy 0.752 minus Fy 0.748. And this is nothing but phi of, you should take with this with respect to the mean. The mean is 0.75. Mean is 0.75. So 0.752 minus 0.75 divided by the value of sigma. So it is x minus, rather y, because we have Fy here, y minus mu y divided by sigma y is what we need to write here for this one. Similarly, for this also, y minus mu y divided by sigma y. So both you write there. Now this and this can be found out from the tables straight away. Okay, rather this is found out from the table. 1 minus of that value. That means for this we'll get this value, and 1 minus that value will give us this value, and hence that will correspond to that. Okay, phi of minus x is equal to 1 minus phi of x. Both these values are same magnitude wise, but sign is different. So phi of minus x is equal to 1 minus phi of x, or phi z is equal to, phi of minus z is equal to 1 minus phi z. So if you see the tables, you'll get for 1.5385 this value from the Gaussian, tables. From the Gaussian table, you have to get that, and you'll get the value which is, after subtracting, you'll get 0.8760. So this, it has to be found from the normalized Gaussian table. Okay, normalized Gaussian table. So you'll get here 87.6.8760, that is 87.6. Okay, of the PCBs will lie within the tolerance limit if we have the what you call range as this value, or tolerance as this, with mean as this, and the standard deviation of this. The result will turn out to be 87.6, printed circuit boards within the tolerance limits. So now let us have a look for a case where the function y is equal to gx has a negative slope. Similar to the previous analysis, we will take x to be a random variable and let that y is equal to ax plus b. So if you have a negative slope, then a will be less than 0 now. In this case, we require a to be negative. The inverse relation is, again, inverse relation will be same. Earlier we took a greater than 0, that is slope is positive. Now we are taking slope is negative. So if you see this figure over here, this slope is positive. Okay, the slope of this line is positive because a is greater than 0. Now we are considering a less than 0, therefore the slope will become negative like this. So fyy is equal to p of y less than or equal to y, p of x greater than or equal to y minus b by a. Now, because this is, the value of a is negative, then you'll have a negative quantity here. And for that, we need to write 1 minus p of x less than y minus b by a, and that is 1 minus fx y minus b by a. So it will be almost similar to whatever we considered for the case of phi of z, phi of minus z is equal to 1 minus phi of z. Similar to that, because the value of it is negative, we need to write 1 minus fx y minus b by a, because the value of has become negative now. Okay. So the plot for this will be like this, because now a is negative, the slope will be negative, and hence we need to write like this. So hence again, region where y is less than or equal to y, and region where x is greater than x is written over here. Okay, this and this. Okay. And the relations, that is the forward relation and the reverse relation, inverse relation, is what is mentioned over here. So now when we try to take the what you call want to find the PDF of the function, the value, the what you call variable y, where y is equal to g of x, then we'll get fx y minus b by a, and because the slope is negative, we'll get minus 1 by a, whereas a is less than 0. You can't have the probability equal to negative. So note that 2.104, the factor 1 minus 1 by a is positive quantity, because by assumption a is less than 0. So because a is negative, we should have minus 1 by a, because that will make it positive, because of the reason that the probability cannot be negative. So thus fyy is always greater than or equal to 0, as it must be, because probability of the PDF is always positive. So let us take, one more example over here. Suppose that we take x is an arbitrary random variable, and that we take y is equal to gx in the form of y equal to ax square, where again we take a to be positive. Okay. Then the inverse function of this must be specified in two regions, one for x greater than 0 and another for x less than 0. If y is equal to ax square, then x is equal to I need to take y by a, and x will be x square is equal to y by a. X will be equal to root of y by a. X square is equal to something more has happened. So if you see over here, right, for x square will be x will be equal to root of y by a plus or minus root of y by a, and hence we'll get the value which is something like this. And in this case, you can have for both x less than 0 and x greater than 0. So now following the same process, so here y is greater than 0, a is greater than 0. For the given y, we can identify the regions along the x-axis for where y is less than or equal to y. The only region of interest in this example is the region where y is positive, because negative values of y cannot be mapped onto the x-axis. If you take negative value of y, then x will become naturally the imaginary case, and hence we might not be taking that. So now, this, if you try to write the curve for this, then we'll get either x equal to root of plus or minus y by a, or y is equal to ax square. Y is equal to ax square is a parabola, and that parabola curve will be like this. Okay, so where you can write the y is equal to ax square, region where y is less than y is this, and you have region where that x takes the ranges from minus of root of y by a to plus of root of y by a, and that is what is written over here. And the inverse equation also can be written, which is either of these two. In this part, it will be x equal to minus of root y by a. In this part, it will be x equal to plus root of y by a. So that means positive portion separately and negative portion separately. Okay. So using the inverse relation in 2.106, we can identify the region on the x-axis for this maps into. So now we need to write both the regions, that is minus of root of y by a less than or equal to x, less than or equal to plus root of y by a. So the value of, you have two different things, fx of plus root of y by a minus fx of minus root of y by a. So having the what you call CDF like this, we can find the PDF by just differentiating this function over here. So we'll get fyy is equal to fx, small fx of the same quantity, and internal derivative of this. Internal derivative of this is 1 by 2 root of ay. Okay, this is root of y by a. So each time you'll get internal derivative here, internal derivative will be like this. Now this quantity is, differentiation will be this, and the internal derivative of this. Internal derivative of this is minus 1 by 2 root of ay. So minus into minus will become plus now. So 1 by 2 root of ay, fx plus y by a is equal to plus of fx minus of y by a. Okay. So this is as far as we can go with this example, unless a specified PDF fx is introduced. Once a specific value of fxx is given, then we can find the value of fyy. That is what it shows over here. So you can have the computer simulations which play a very good role, and you can try to plot for different plots, right? And let us not go very deeply into this. This is just for showing sake, where we can use in the MATLAB the function which is known as URNG, which is in the interval 0 to 1 random value generation. Okay, the uniform random value generation, random number generation is what it is showing, and from that again you can try to find out the value. So we can take another example wherein you can take x to be uniformly distributed between 0 and 1, where we can take fxx is equal to x, 0 less than x less than or equal to 1. This is most important. The other part of it is just unnecessary, because this is equal to 0 between this and 1 above the value there. Okay, fxx is equal to 0, minus infinity less than x less than or equal to 0, x 0 less than x less than or equal to 1, 1 for this fxx, it should be 1. Okay, because above certain value, above this range, it will be the total probability itself which will turn out over here. So given y, we identify the region on the y-axis where y is less than or equal to y. For the same y, we can identify the region on the x-axis where x is less than or equal to g inverse of y. So we can try to write, we can connect random variable x and y with fyy is equal to p of y less than or equal to y, and that is x less than or equal to g inverse of x. So this g inverse of x will give us fx of g inverse of y. We can write here fx of g inverse of y. So whatever is given there, you'll get that value. So for the CDF fxx, where you have 0 less than x less than 1, we have the value of fyy as the value of x itself, and that is equal to g inverse of y between 0 less than x less than or equal to 1, because of the uniform distribution which he has taken over here. Okay, this quantity will be equal to this only, x only, okay, between 0 to 1, so which he has taken here. So this is the algorithm that we are looking for, and we write it in the inverse form as y is equal to gx is equal to fy inverse of x. Y is equal to gx equal to fy inverse of x. This is the standard algorithm which we will write over here. So let us take examples corresponding to this. Suppose that we want an algorithm to simulate observations of the random variable y with parameters lambda greater than 0. Do we have time? Let me see whether, okay, only one page we have. We'll finish with this. So we know from 2.20 that CDF for the exponential random variable, fyy is equal to 1 minus e to the power of minus lambda y greater than or equal to 0, and 0 for y less than or equal to 0. So what is important is this range where it exists here, it is equal to 0. So using this CDF, which is there over here, you can easily find this relationship. This is equal to x because we are considering what you call the value there, fyy, and then we'll get this if you just take this x 1 on this side and minus also on this side, then it will become 1 minus x. Of this you take this side and this you take this side, then it will become e to the power of minus lambda y is equal to 1 minus x, and that will give us minus lambda y is equal to logarithm of 1 minus x, and y will be equal to minus 1 by lambda logarithm of 1 minus x when x is taking the values 0 and 1. So this is the desired equation which we have. We need to solve the problems corresponding to this. We'll try to solve the problems in the next session. Please join the next session once the time is over, right? So